The third part, CHOPS. CHOPS and related technologies. CHOPS comprises the deliberate imitation of sand in flux during the completion procedure, maintenance of sand in flux during the productive life of the wire, separation of the sand from the oil, and finally the disposal of the sand. No-sand exclusion device screens liners gram packers are used in wearables, and no filters, cyclones, or high-pressure separators are used as the surface. The sand is produced along with oil, water, and gas, and separated from the oil by setting before being cleaned and sent to facility for upgrading to a synthetic crude. To date, massive sand influx to increase production rate has been used only in unconsolidated sand reservoir containing viscous oil, almost exclusively in the Canadian HOB, and in shallow, low production wells. Because of the starting economic success of CHOPS in these difficult conditions, the concepts behind sand influx management are to be to a considerable degree beginning to be implemented in other oil production processes and are even affecting the industry's view of how to develop a natural gas resource. The cavity completion approach developed for coal bed methane exploration is a very similar process to CHOPS, carried out for very similar goals to increase well productivity by enhancing fluid flow capacity in the region around the wellbore. With this technology, which will soon be used in development of methane from Canadian coal seams, deliberate production of 20 to 100 of coal from the formation during well completion creates a cavity and generates a surrounding zone in the coal where natural fractures are open. These wells immediately become good CH4 producers, in contrast to wells completed with conventional methods that may produce water for months before economical CH4 production begins. In conventional CH4 production from coal, the natural fissures must dewater before gas can create a continuous flowing phase, and this also requires shrinkage of the coal as the methane in the near wearable environmental is depleted of the gas. The large radial cavity and this picture shows us a cavity completion in a coal seam. The cavity is created so that the rock is damaged. The high drainage surface area and open fractures and accelerate gas drainage. Perimeter in the plot are schematic along the middle plane in the stratum. Surrounding perturbed zone give a large wear effect, and in general, the productivity of a large wear compared to a similar diameter wear is approximately proportional to the natural logarithm of the radial ratio. Cavity completed massive wears in coal are generally better producers for their entire life, and also may have episodes of the co-production during their life, usually for short periods. In this sense, there is a further similar to CHOPS wear. The concepts developed in CHOPS in Canada in the period 1988 to 1995 have begun to diffuse into conventional oil production from sandstone, traditional in conventional oil production from high-rate oil and gas well. Exclusion of sand as a variable has been the norm. Sand exclusion methods, most of which have been tried at one time or another in the Canadian HOB, with no success, may include selective perforation approach using small diameter, deep penetrating charge, careful perforation, orientation, and avoidance of perforation in the most sensitive strata. Control of the flow rate of the wear, so that sanding is not inefficient. Various types of screens, lot liners, screens, wear-wrap screen, and special pre-pack filters, gravel packers wear, internal placement of coarse grain sand, or replacement of gravel into the perforation channels outside the wear bore. Various types of hydraulic fractioning methods often use resin-coated sand, such as ARCO frac and frac and pack, high-rate high sand content fracking with high pressure to pack sand into the variable region. Resin injection, where a special colloidal suspension of epoxy or other approach involved delay chemical reaction or sodium silicate injection is pumped into susceptible beds to generate cementation at the grain contract to strengthen the sand. Recent work has clearly demonstrated that conventional oil and gas wells, if properly managed and monitored to control risk, can produce bursts of sand that clean up and unblock the near wearable region without significantly increasing the chances of wear impairment. In a 5-year period in the North Sea, over 200 wells have been converted to this approach. On average, such wells produce at 35% higher rates, and because these are high-rate wells to begin with 1,000 to 3,000, the financial benefits are huge. The idea was generated in the early 1990s based on preliminary experience with CHOPS in Canada. Now the concept is being tried elsewhere in the world, usually to the benefit of their production rates. The cross fertilization of ideas arising from CHOPS and other Canadian techniques has great benefits in the world oil industry more than is appreciated. This influence will continue, and some of the possibilities generated in Canada that are already feasible for export are listed here. Pressure passing technology can be used with conventional oil to increase flow rates and to help stabilize water flows against excessive fingering. Inert gas injection, largely pioneered in Canada, can be used in conjunction with horizontal wells to revitalize old conventional oil reservoirs to increase total recovery. Secondly, VAPEX and various combinations of this method can be applied to other heavy and intermediate oil deposit up to 30 degree API. Heavy oil upgrading technologies being perfected in Canada can be implemented in other heavy oil beneficiation facilities around the world. New waste disposal practices such as slurry injection of produced sand can provide better environmental protection. Sand management applications can be applied to in conventional oil and gas wells to increase production. History of CHOPS development. History of sand production in Canada heavy oil. The first discoveries in the Canada heavy oil belt were made in the area in the late 1920s. Heavy crude oil with a high asphaltance content, an ideal feedstock for asphalt products, has been produced since at that time. Typically, small diameter perforations 10 to 12 were used in these heavy oil wells to access the reservoir. However, the reciprocating pumps that were available were limited by slow rod for velocity in the viscous oil in the tubing, and these wells achieved a maximum of 8 to 10 meters per day of production, usually less. Many wells produce at as little as 10 to 15 bottles per day. Towards the end of their productive phase, and reservoir extraction efficiency seldom exceeded 5 to 8% of OOIP. Operators in the HOB soon discovered empirically that they had to cope with small amount of sand entering the wellbores along with the oil, about 1% in the more viscous oil with the slow production rates and the small diameter perforation used before 1990. The small local operators learned that wells that continue to produce sand tend to be better oil producers, and the efforts to exclude sand with screens usually led to a total loss of production. They learned to separate the sand and most of the water from the oil by gravity segregation in heated vertical stock tanks before shipping the oil by tanker trunk to the small local upgrading facility in actually mainly asphalt production facility or to refiners in Edmonton and Regina. The operators spread the waste sand on local gravel road, and in some areas the roadbeds are now up to 1.5 meter higher, courtesy of repeated applications of sand. These macro-engineering improvements advanced slowly for 50 years because the profit margin on heavy oil was always low and the demand was limited because most refiners could not accept even small amount of the sulfur-rich viscous feedstock. The sharp oil price increase in the 1970s and 1980s led to great interest in the HOB resources. Many national companies were attracted to the area. They introduced the latest screen and grab packer technology and even developed new technologies for screens, such as the Texaco steel wool pack screen. However, in all cases, sand exclusion resulted in greatly impaired productivity or total failure to bring the well on production. Hydraulic fracturing techniques of all types were tried. Even injection of pea-sized gravel into the formations. All of these attempts failed. Wells were sometimes stimulated with a large slug of steam or superheated hot water to increase near wearable mobility. After a few days of enhanced production, well productivity generally returned to very low rates. To this day, there are hundreds of inactive wells with expensive screen, gravel packers, and hydraulic fractured gravel placements that were carefully installed. The higher oil price that developed in the period 1973 to 1983, along with advent of progressing cavity pump in the 1980s, changed the non-thermal primary heavy oil industry in Canada. The first PC pumps had a short lifespan and were not particularly cost-effective, but better quality control and continual advance led to longer life, fewer problems, and widespread acceptance in the 1990s. The rate limits of beam pumps were no longer a barrier, and operators in the period 1990 to 1995 changed their review of their management. Sand began to be viewed as an asset because more sand means more oil. Individual well productivity began to rise above the traditional average. The goal of the completion and workover strategy gradually become more clear. Do what is necessary to initiate and maintain sand influx, new workover methods, better pumps, and new completion methods mean that old inactive fields that had only produced 4 to 6% of OOIP could be profitably rehabilitated. These efforts are continuing at present, extracting more value from old fields than was thought possible even a few years ago. Along with PC pump and much higher sand rates, a new set of issues began to arise. Management of the sand and some other waste streams become paramount, and new macro-engineering developments have taken place to control costs and to minimize environmental impact. More highly integrated sand management methods have been developed, and new methods of coping with sand separation and disposal implemented. CHOPS is a new production technology that is still rapidly developing. New issues and better methods are being addressed, such as optimal workover strategy, different sand disposal practice, implementation of improved recovery methods, water flooding pressure plus passing, along with chops and hybrid of several production technologies to increase recovery. Given the low operating cost and the recent have been achieved, and given that thermal energy requirements are zero, interest in chops as a primary production method is substantial. Also, it appears that the only serious limitation on the amount of oil in the Canadian HOV being produced by CHOPS in the year 2001 is the lack of upgrading capacity. Current CHOPS data worldwide. To date, CHOPS has achieved wide utilization only in Canada. However, anecdotal evidence suggests that heavy oil operators in California traditionally took no step to exclude sand, realizing that screen and sand packs would simply become blocked and production would cease. In the dairy field, heavy oil is produced by thermal methods, and large amounts of sand accompany the oil. In China, CHOPS has been tried with some success in the Nanyang oil field from 1997 to 2000, but was not permanently adopted. In the Liaohe oil field, trials were also conducted under challenging conditions and continue to be attempted in reservoirs that are not as favorable as Canadian reservoirs. In 2001, Jilin oil field initiated a CHOPS project in a heavy oil deposit in 300 meters deep fine grained sand in the northwest part of the province. Although rates are modest in comparison to Canadian production, they are far greater than sand-free or thermal production rates. Broad region acceptance of sand influx as a valuable mechanism for enhancing production has not yet taken place in the industry. Despite current production level of over 70,000 meters per day in Canada. The reasons are the fear of sand influx in producing asset that could impair production, the non-traditional nature of the production mechanisms, difficulty in production predictions when sanding takes place, complexity in properly implements CHOPS, and the need for sand management strategy that can cope with large volumes of produced sand. Furthermore, CHOPS wells require repeated workover and more effort to sustain economic production than conventional oil wells. Typical airbed reservoirs. Heavy oil development using CHOPS in airbed takes place largely in the HOB, with a small amount of production generated in the region to the west and southwest of the Cold Lake. Deposit with the exception of a few geologically older fields. All the heavy oil used as reservoirs in airbed are found in lower and middle Marley group. The Marrow group of the formations is an underformed and flat-lying middle Cretaceous clastic sequence comprising sand, sites, shales, a few coal seams, and some thin concretionary beds. The depositional environment ranged from channel sands laid down inside the valleys, caved several tons of meters into the underlying sediments to estuarine accretion plains formed by lateral migrations of river channels in a flat terrain to the deltaic, shallow marine and offshore basins. During the Middle period, what is held to the HOB was low-lying land near the coast of the shallow inland sea. To the northeast lay of the Canadian Shield, a low relief terrain made up of granites and rocks, but few sediments. This area contributed some of the sediments in the Módulo group, particularly to the lower reservoirs in the sequence, which are mainly alluvial sediments, such as Colossus River channels. The sea coast gradually rose and moved from the northeast to the southeast, and fluctuations in the sea level also took place. The major sediment source shifted to the south and southwest, where weathering and erosion of older sediments contributed finer grained materials such as silts and clays. Volcanic activity in the southwest, where the Rockies currently sits, contributed volcanic ash, which turned into smectic clays and eventually formed the high porosity swelling shales found throughout the Canadian West. The sediments of average become finer grained higher in the sequence because of the depth of water gradually increased during the Módulo group sedimentation period. The lower and coarser grained part of the Módulo group, which contains almost all the heavy oil reservoirs in Canada, was eventually overlain by a thick deposit of clays. This thick and regional continuous shale sequence, called the Colorado group, which can be traced all the way from Texas to Alberta, and on the north of the river valley. After a burial under a sedimentary cover that was about 500 to 700 meters greater than present, the region underwent slow uplift and erosive processes have acted until the present time. The oil invaded the reservoirs from the deeper in the Western Canadian sedimentary basin and become viscous through two processes: the loss of later volatile and the increase of more molecular weight because of bacterial exit. This took place as the oil-bearing strata were exposed to more shallow waters, and the end product of the was viscose oil with only CH4 present at the light molecular weight phase. Galactation in the last millions years resulted in continual erosion and the exposition of thin veneer of sedimentary. The present depth of barrel of CHOPS reservoirs ranges from 350 to 900 meters, both in the HOB and in the heavy oil region west and southwest of the Cold Lake deposit. The sedimentary have been buried much deeper than the present, so they are over-compact with respect to present condition. The layer of the sand bodies range from quiz to lacertes and arcoses, with smaller amount of quiz and more feldspar grains, shear grains, and volcanic glass shards. The more mature sand and base of this group tend to be more quartzose and coarse grain with the major sediments sourced from the Canadian Shelf. In the more mature quiz sand and base of screens, and in the thick channel sand higher up, the clay contents can be less than 1%, but they can be as high as 10% in fine-grained lacertes. Thin clay seems less than 100, think and common in many areas, and these clays seams are apparently largely produced in disaggregated form, along with the sand in CHOPS wells, although large block and undoubtedly left behind around the world. Some reservoirs have large shale seams within the producing zone, and breaking apart of this shale during production can cause problems. Oil production is from a variety of reservoirs that may range from an extensive 3 to 5 meter thick blanket sand to a 35 meter thick channel sand with sinuous trees to no wider than a kilometer. In many areas, up to 3 reservoirs may be intersected by vertical well. These sand bodies are from 30 to 90 meters apart, separated by intervening water saturated seals and clay seals. They are all UCSS with a porosity of 28 to 32% and permeability of 0.5 to 15 deci, depending on grain size. The highest permeability value reported are for gravel seams that are sometimes found in river channel deposit. Most CHOPS reservoirs have an average permeability of 1 to 4 dAs. It is impossible to obtain from Albert UCSS heavy oil reservoirs because gas X solution leads irreversible core expansion. Therefore, the porosities of the reservoirs are back calculated from geophysical logs, and permeability are back calculated from Greenside's correlations and limited number of well tests. A typical CHOPS stratum is a 5 to 12 meters thick fine to medium-grained unconsolidated sandstone. Bears a depth of 500 to 650. The sand grains have an average grain size of 80 to 150 microns. The permeability of the sand is about 2 dAs, which is a related high permeability for an oil reservoir. The saturation of the pore space is about 87% viscous oil and 13% connate water that contains about 6,000 parts per million of dissolved salt. There is no free gas in the pores of the sand. The initial pressure in the reservoir is about 4 to 6 ampere, and reservoirs are most often somewhat under-pressured. This means that the pressure in the reservoir is somewhat less than the pressure that could be exerted by a continuous column of water to the surface. Taking this as the mean unit weight of water, generally it is found that PO, where Z is the depth, the density of the water in the pores is on the order of the 1.04 to 1.05, becoming nearly twice as salt as seawater. In most cases in situ, the oil is above 90% saturated with CH4 dissolved into the liquid oil. The reservoir temperature is 20 to 25, and the viscosity of the oil is the range of 1,000 to 12,000. Topical CHOPS were behavior summary. CHOPS wells display great variation in their production histories, depending on a wide range of factors that will be discussed below. The major aspects of a typical CHOPS well are when a new well is completed, initial sand influx is large, typically as high as 10 to 40% of the volume of the produced liquid and solid, over a period that can be as short as a few days or as long as several months. The high initial sand production rate gradually decays toward a steady state influx rate of 0.5% to 10%, depending on the oil viscosity. The oil production rate increase toward a maximum 7 months or more after placing the well on production, and then slowly decades as the reservoir depletion effects begin to dominate and there is less reservoir energy available to the well. Continuous gas influx characterize all CHOPS production, giving a product at the surface that is charged with CH4 and 4. This figure shows us oil and sand production profiles for a typical CHOPS well. Short-term sand and oil production rates appear to fluctuate chaotically about the mean long-term value, but time average production rates follow the general pattern of figure. A successful workover can partly re-establish oil and sand rates, but generally the workover does not raise production to level as high as in the first cycle. This liquid flux pattern is radically different than conventional well behavior. Because there is a peak in the oil rate curve, there must be at least two counteracting physical mechanism with different characters effects. The two dominant competing processes are considered to be increasing their productivity because of the enhanced fluid conductivity generated around the wellbore with continuous sand production, and the diminishing their productivity because of the gradual deletion of reservoir energy. These two effects combine to give a peak production, followed by the gradual decline and the depletion effects to be dominant with time. This chapter will qualitatively explore the physicals of this unusual behavior, a technical issue that arises in CHOPS implementation will be reserved for the next chapter. This figure shows us the delay peak indicates at least two coexisting physical different mechanisms in CHOPS well. It is important to emphasize that CHOPS in Canada is approaching the status of mature technology. Reasonable oil production rates can be achieved, and most of the major technological problems appear to be solved. Nevertheless, continual macro-engineering advances that increase efficiency and reduce OPEX are still taking place. Because of the advent of CHOPS, primary heavy oil production in Alberta is no longer limited by technical production constraints. The writer is convinced that CHOPS production in Alberta alone could raise by 80,000 to 100,000 barrels per year for several years if stable demand and good returns to producers are sustained. This undoubtedly could also require the additional upgrading facility. CHOPS production behavior. The term CHOPS refers specifically to heavy oil production from unconsolidated sandstones with deliberate initiation and sustaining of sand influx into the well. Not only are well completion and lifting practice different from those for conventional oil, but an entire era of novel materials handling practices have evolved to cope with sand influx and disposal. Production approaches remain based on practical considerations driven by field performance data, because CHOPS does not yet rest on a theoretical base that allows a period predication of oil and sand rates from first principles. The role of experience is vital. The experience in Canada resides in the tradecraft and practical activities of thousands of engineers, technicians, and field operators in dozens of producing and service companies. Different views of best possible practice exist in different companies. The distillation and the presentation of empirical and practical knowledge is far more difficult than the exposition of a theoretical model. Any attempt to do so, as in this report, will be incomplete and in some cases incorrect in detail. None of the large integrated multinational oil companies currently have significant activity in the non-thermal Canadian heavy oil industry. Rather small companies with a simple horizontal command structure have generated the majority of the recent developments and experience base in new heavy oil technology. Field personnel are usually encouraged to take the initiative in addressing practical sand management and production problems. It is clear that the day-to-day practical aspects of CHOPS have been conceived and perfected in the field, not in the laboratory or in front of a computer screen. Many of these practices unfortunately remain inadequately documented. Production profile. A well production profile for 3 production cycles is shown in figure, and major features are the following. Immediately after initial of oil sand follow in a CHOPS where the volume fraction of sand is extremely high, often as much as 30 to 45% of the total produced liquids and solid volume. This initial elevated sand rate is reservoir and viscosity dependent. Low viscosity reservoirs may peak at 20% sand. High viscosity reservoirs with high gas contents may show peak sand rates exceeding 50% by volume of the total produced sand, oil, and water. The sand rate tend to drop over a period of weeks or months to a value of 1% to 8% of the total volume of liquids and solids, depending on the viscosity of the oil. The figure left shows the CHOPS wear behavior over 3 production cycles, separated by the workover to maintain sand influx. And the right one it shows the steady state sand rates as a function of heavy oil viscosity. More viscous oils produce higher sand rates. In the more viscous oil, there is often a prolonged plateau for several months at rates of 10 to 20% before a decline to a steady state rate of 2 to 6% that may be sustained for many months or even for several years. The oil rate starts at a level that is related to pumping practice, reservoir viscosity, and the amount of gas in solution in the oil after the present time. This rate and its evolutions are not predictable on ground using material mathematics models, physical spaces equations, or scale laboratory studies. Production ignition rates of 10 to 30 are common, but in the phase, oil rate may be controlled as well by torque limit on the PCP. Low speed are necessary because of high torque from sand content, and this limits the production rate. The oil rate generally climbs over a period of several months, reaching a peak production rate that may be 30 to 60% higher than the initial rate, exceeding 50 in the best wells, but more commonly in the range of 20 to 40. After the peak oil rate is passed, well usually display a gradual decline in production, but this also depends in part on pumping strategy. If a pre-decided value of oil production rate is used, it is often feasible to sustain well productivity at this level for many months or even years. Although well annulus fluid level and pump speed will have to be adjusted as the reservoir conditions change. After a period of production that may last from a year to several years, the well gradually approach a production rate that is no longer acceptable to the operator. At this point, a workover is initiated to attempt to establish a higher production rate. The post-workover behavior in successful cases is similar to the first cycle of production, but very rarely achieve the peaks and rates and production rate of the first cycle. Exceptions to this occur if the well is perforated during the workover with a large diameter and more closely spaced pots, a common practice for the redevelopment of old fields from the pre-CHOPS area. About 85% of the wells follow this production history. However, there are many exceptions, including cases where sand ignition is not possible. Cases where water influx is early and massive, this appears to be highly dependent on the field and the well position with respect to water saturated zones. The closer of the well is to achieve bottom water, the greater the risk of early water influx. Case where early destabilization of the shear overburden causes loss of the well. This occurs mostly in the more viscous reservoirs when extremely aggressive production is attempted. Causes where the oil production rate declines rather than increases during the initial heavy sand production phase, a response that is usually accompanied by gradually increased water production. Causes where the production profile are amountless for unknown causes such as premature perforation blocking, lightly cemented sand, and it's hard to establish too much lost circulation material force into the reservoir during drilling, or over use of cement during casing cementation. For various reasons, CHOPS there may experience mechanical failure or productivity drop, and workover is then required to re-establish an economic level of oil production. Many workover choices are possible, which is used depends on the operator assessing the reason for the well productivity loss. A CHOPS well may experience a number of workovers during its life, and each workover usually results in a surge of oil and sand production through diminution in magnitude with each cycle. Some wells produce for years without a need for workover expect to change the PCP. Other wells require repeated workovers to sustain economic production rates. Figure 3.6 is an attempt to show this behavior over the life of the wells that have encountered different production difficulties. Sand and oil production rates in CHOPS wells fluctuate substantially on a short-term basis, and for production rate evaluation, it is necessary to take a series of simple or to take a long-term average. Water ingress is a common factor in the decline of well productivity, and one of the for the selection of reservoirs are suitable for CHOPS is absent of a mobile water zone. Lateral inversion of water from the considerable distance even has been a problem in some reservoirs, even if no active bottom water was detected in the individual wells during the geophysical logging evaluation. There remains debate as to whether more moderate production practice in CHOPS well would increase the oil recovery factor by delaying lateral calling or reduce profitability for unnecessary delay of production. The two options are implementing a less aggressive drawdown during the early phases of production. This figure shows CHOPS wear history can be widely variable depending on several reservoir mechanisms. This picture shows water ingress can prematurely ruin CHOPS oil production. Capping the production rate deliberately at a value below the maximum short-term rate that the wear can sustain. Water ingress can be rapid, with the wear going from a few percent to 100% water production in several months, or slow, with a gradual increase of water cut over several years. In spite of CHOPS being a high process, some CHOPS reservoirs are characterized by producing wells that have operated for over a decade without significant water cut increase. In these cases, it is supposed that active water is totally absent, or that any active water is so far away that the pressure decline in the producing well never affects it. As yet, it is not possible to make rigorous scientific or empirical predictions of well behavior with respect to water ingress behavior. It is necessary to do careful geological studies. Even then, there is a great deal of uncertainty. Comprehensive analysis of the large public domain database for dozens of reservoirs and thousands of wells could generate considerable insight into this question, but no company or agency has yet undertaken this task. Furthermore, since many older wells have been modified in the period since 1992 to take advantage of CHOPS methods, it is difficult to carry out such an evaluation based on the public production records alone. Corporations do not record all relevant production factors, or do they record sand cuts or gas oil ratios in a standardized manner for the public domain. Old fields that were abandoned with the wells left intact can be converted to CHOPS if the company finds it feasible and if the old wells are in reasonable condition. Other fields remain on slow production with beam pumps because the company does not need the additional production capacity that comes with CHOPS, or does not want to incur the capital cost of conversions. Conversion engenders a cost of nearly 65 million, including several charges of PCP and perhaps formation, stimulation, conversion of a number of old fields in the proposed area and to the south of oil field took place in the period and slowly continues at this time. New fields such as Egg Point have never experienced a slow phase followed by a conversion to CHOPS and have been on stable production at economic rates for up to 10 years. Many operators are currently planning or carrying out drilling programs to place new wells in old fields, dropping the well spacing to 10 acres from 20 acres, and even in some where individual well production is good and there is a sink oil zone down to 5 acre spacing. There are also continued activities to develop previously no developed fields and to redevelop old wells through novel workover approaches and better pumping methods. Some field operators claim that each field is different, whereas this statement is obviously correct. It can also lead to a counterproductive attitude. If all fields are different, why bother seeking generalizations and doing things? There are substantial differences among fields, but there are also major commonalities, particularly in terms of less topography and reservoir conditions and the physicals of CHOPS process. Operators who understand the physicals of the CHOPS process tend to be most successful. Typical sanding rates in Canada wells and fields. A CHOPS well produces its highest amount of sand in absolute terms and in relative terms during the days and weeks after it's brought into production on the first production cycle. Therefore, younger fields produce more sand than older fields. An exception to this arises in other fields where new PCP technology is implemented after some years of reciprocating pump exploration or perforation of wells and more aggressive production practices are instituted to deliberately promote sand influx. The maximum amount of sand generated in any single year in Canada was nearly 330,000 in 1997, but this will likely be exceeded in 2001 because of aggressive drilling programs for new wells undertaken in 2001 by the industry. Likely more than 200,000 of sand will be produced in Alberta in 2001, or any aggregate volume of nearly 2% of the total heavy oil produced by CHOPS method. Because of wide differences in water production, well productivity, and methods of reporting sand rates, it is recommended that sand rates also be recorded as the volume of sand per volume of oil. Although most operators record sand only as a percent of gross fluid produced, the sand cleaning truck operators measures the value of sand in stock tanks when they clean them, and the amount of produced oil is calculated from truck tickets for the wells, or on the basis of test separator trials on individual wells. Given that more viscous oil will produce more sand, sand production as a percentage of oil production is not consistent over the HOV. In the southern part of the HOV, the average viscosity is often below 1000 cp, and the amount of sand produced is from 0.5 to 1%, perhaps less in some cases. For the long horizontal wells used in Pelican and Amber fields to the west of Cold Lake, fine green sand enters through the production screen at volumes rate of 0.25% or even lower. The oil viscosity is only 200 to 1000 cp in these fields, and therefore both CHOPS and non-summer horizontal wells are economical. In the viscous oil of large lean birds and ELK Point fields and other fields to north of where the viscosity generally exceeds 5000 cp. Oil production rates from CHOPS are lower than the low viscosity areas, but the sand percentage approaches 4 to 6% in productive wells and 2 to 4% in less productive wells. In CHOPS trials in highly viscous oils between 15,000 cp and 40,000 cp, 6 to 10% sand. Steady state oil production is not uncommon. Thus, a single CHOPS well producing 30 to 35 of oil of viscosity 1400 cp will produce nearly 0.5 to 1.5 of stock tank sand per day. The CHOPS were north of field in 10,000 cp oil producing at the high rate of 15 per day will produce about the same amount of sand and about 1 per day in the aggregate, given that there are many CHOPS wells that produce only a few cubic meters of heavy oil per day. The industrial average amount of sand per well will be nearly 0.3 to 0.5 per well per day. An operator of a field with 200 wells producing an average 12 meters per day of 2000 cp oil must cope with 18 to 30 per day of sand, or from 6,000 to 10,000 per year in the highly viscosity oil of the Limbers field, where average well production rates are perhaps 6 to 7 meters per day. 500 activity wells will produce 40 to 50,000 meters per year of sand. What constitutes of CHOPS project? CHOPS is a single well technology. It is not necessary to have a pattern of wells, such as in steam injection processes. Apparently, no significant benefit occurs to an individual CHOPS well because there are other similar wells surrounding it. Because each well has its own stock tank that is emptied by truck. There are no economics of scale to be achieved in folding many wells into a single large facility. Therefore, in the limit, a CHOPS project could even be defined as a single well. However, in practice, more and more CHOPS fields are being developed using pad development with from 3 to 10 wells drilled about from the same 1 to 3 acre site so that the number of roads and the length of service corridors can be optimized. Furthermore, consideration is always given to the capacity of local facilities such as batteries to clean the oil. If a company has a battery with a capacity of 20,000 barrels per day, then the company will target sustaining nearly 300 wells, each producing on average 70 barrels per day. Small local operators must deliver their oil to batteries that can accept it. And the battery capacity in the industry is limited to what can be shipped to local upgraders or similar facilities in the United States. There are local operators in the field who operate only 10 to 20 wells, although the great majority of the projects in the specific field by one operator involved large numbers of wells, up to 400 to 500 wells in the Limbers and Yerkes Point fields. Thus, there is no minimum size for a CHOPS project, and the maximum size is usually controlled by the capacity of the batteries and the local facility.